another paper, another lecture, Probability and Statistics Part 2, actually, Probability and Stats 2, May June 2021, Variant 63. Let's get started right away. Let's read the first question and then we will label it with the proper topical name. The question says that we have the number of goals scored by a team in a match is independent of other matches. So that's the number of goals scored by a team in a match denoted by the random variable x, which has a Poisson distribution with mean 1.36. A supporter offers to make a donation of $5 for the team to the team for each goal that they score in the next 10 matches. Find expectation and standard deviation for the amount that the supporters will pay. So now let me denote this thing that we'll be working for as y. And what is x? X is the number of goals scored. So 1.36 multiplied by 10, that is 13.6. X follows a Poisson distribution with 13.6. It is a property of Poisson distribution that expectation of x is lambda, so is the variance of x. So therefore, expectation of y, but even before that, what is the relationship between this variable y and variable x? You will get $5 per goal. The more the goals, the more dollars would come in. In other words, y is equal to 5x. This is the equation that we were striving for. So when y is equal to 5x, expectation of y is expectation of 5x. That is 5 times expectation of x. That is 5 times 13.6. And we use a calculator and we get this answer, that is 68. And naturally the units are dollars. Similarly, variance of y is variance of 5x. So let me write this 5 correctly. That is 5 square times variance of x. That is 25 times 13.6. And we multiply, we get this answer as 340 and the units are dollars. Actually, for variance, it's dollars square. The unit of standard deviation will be dollars. What is standard deviation? That is square root of variance. So that is square root of 340. And this comes out to be $18.4, correct to 3 significant figures. So the first question was conceptual. It was about Poisson distribution. At the same time, the concept of linear combination was there. So it was linear combination with Poisson distribution. Let's move to the next question. The next question is about, in the past, the time in hours for a particular train journey has a mean such and such. It has a mean of 1.40 hours and a standard deviation of 0.12. That's the time in hours. Following the introduction of some new signals, it is required to test whether the mean journey time has decreased. First of all, what is meant by type 2 error? Then the mean time for a random sample of 50 journeys is found to be 1.36. Assuming the standard deviation is still 0.12, test at the 2.5% significance level whether the population mean journey time has decreased. So let me do the calculation part first. First of all, you would write x follows a normal distribution. This is 1.4, 0.12 square, 1.4, 0.12 square. And since it's a sampling question, the mean is divided by 50. That's the first thing. Second thing, the sample mean from the data, it came out to be 1.36 hours. What else is there? H0 and H1 that you should always state. Mu is 1.40, mu is less than 1.40. It's talking about decrease. Now let me grab the normal distribution curve because we will be needing it very soon. So let me just paste it over here. Now what is the calculation that we will do? We will do the calculation of z value. Z is x bar minus mu sigma square over n under root, which is 1.36 minus 1.40 divided by 0.12 square divided by 50 square root. Let me grab my calculator, do some calculation, and this comes out to be 2.357, and definitely it is negative. It's a lower tail test at the 2.5% significance level. So this is 2.5% significance level. The z value is 1.96 negative, and this value that we get, let's see where does it lie. So that is the calculated z value. This z value lies in the critical region. So z value lies in critical region. Therefore, the conclusion is reject H0 and accept H1. And what do we have? The question was about that after the introduction of new signals, it is required to test whether the mean journey time has decreased. The answer is yes. There is sufficient evidence. So sufficient evidence to prove that mean journey time has decreased. That is the answer for this one. Now let me do part A. What is meant by type 2 error in the context of this question? What is the textbook definition? Type 2, that is accept H0 when H0 is false. Now when H0 is false, that means H1 is true. When H1 is true, that means mu is lesser than 1.40. We are accepting H0. We are accepting that the mu is 1.40. Now join the two statements like this. So now what is the conclusion? The conclusion is even though the mean journey time has decreased, the manager, the management, or whoever is in charge, the management is wrongly concluding that it has not. Or you would say that those signals had no effect. This is for the last part. So this what I'm underlining, concluding that it has not. So basically for this is what I'm writing. So now this is how you do the first one. What about this one? State with a reason which of the errors might have been made. The rule is simple. If it's in the rejection region, type 1 error has been made. So since we are rejecting H0, so therefore type 1 error would be made. If we were accepting H1, type 2 error, H0, type 2 error might have been made. So in this scenario, the answer is type 2. Now let's move on to another question. Question number 3. It says the local council claims that on average the number of accidents per year on a road, what's happening on that road, is 0.8. Jane claims that the true average is greater than 0.8. That is the claim of Jane. She looks at the records for a random sample of 3 recent years and finds that the total number of accidents during those 3 years was 5. Assume that the number of accidents per year follow a Poisson distribution. State suitable null and alternative hypothesis. That's the first part. H0, lambda, H1, lambda. Test at the 5% significance level whether Jane's claim is justified. Now, average is greater than 0.8, but it's 3 years. So 3 into 0.8 is 2.4. So your calculation is based upon 2.4. Lambda is equal to 2.4. Lambda is greater than 2.4. So that is the first thing that you see. Now, what is the second thing? That is the significance level that is coming up later. That is 5% significance level. What else is there? The sample value is 5. So the sample value of those accidents is 5, and this by default is inclusive. That is the thing. So now it's an upper tail test. Calculate the probability. Probability x is greater than or equal to 5, which is 1 minus probability x is less than or equal to 4, which is 1 minus e raised to power of negative 2.4. This is 1 plus 2.4 plus 2.4 square over 2 factorial, 2.4 cube over 3 factorial, 2.4 power 4 over 4 factorial. So let's double check. That's 1, 2, 3, 4, 5 terms. Don't forget to multiply with this, then subtract 1, and this is the answer that you get. That is 9.59%, because you have to compare it. 9.59%, the calculated probability value, is it less than the significance level? The answer is no, it's not less than significance level. Therefore, do not reject H0, accept H0. That is insufficient evidence to accept Jane's claim. So we don't have that much evidence to accept the claim of Jane. Jane finds that the number of accidents per year has gradually been increasing over the recent years. Show how this might affect the validity of the test carried out in part A2. Now, for Poisson distribution, there are 4 conditions. The mean number of occurrences should be occurring at a constant rate, should be occurring singly, should be occurring at random, and should be independent of one another. All these 4 are for the mean number of occurrences in a specified time or space interval. Now, if this thing happens, that the number of accidents has been increasing, that means this constant rate won't be true. So this won't be true. So if it won't be true, Poisson is not the appropriate model. So therefore, how this might affect the validity? So basically it would be invalid, as lambda is no more constant. So that is the working for this one. Poisson distribution model is not valid. Question number 4. What is this question about? It says the masses in kilograms of flour in a random sample of 90 sacks are summarized. First thing first, that is unbiased estimate of population mean and variance. And then most probably it would be a confidence interval for the population mean. Straightforward, easy marks for this one. So therefore, this is unbiased estimates and confidence interval. So first of all, x bar, or actually it's m over here. So therefore, this is m bar is sigma m over n, which is 4509 divided by 90. Unbiased estimate of population mean is the same thing as sample mean. That's the first thing. Sample variance, that is sigma m square over n minus m bar square. So therefore, this is 225950. That's 225950 divided by 90 minus 4509 over 90 square, and this is the sample variance. Therefore, unbiased estimate of population mean, it's n over n minus 1 sample mean. It's n over n minus 1 sample variance. So that is 90 over 89 into this value. And this value after calculation, the first thing is coming out to be 50.1. So this is 50.1. And this calculation is 0.552. So after doing all this is 0.552. Naturally, they are rounded off values. And if either rounded off or maybe too exact. Now it says, what else? Confidence interval. When we have 98% confidence interval, so just draw a simple number line, and this is 98% in the middle, and 1% at one corner, 1% at one corner. So the z value, we read it for 99%, and that is 2.326. And then we have x bar, which is 50.1. And we have variance, the unbiased estimate, that is in fractions, is 491 over 890, and that's also 0.552. And what else is there? N comes out to be 90. So just apply the formula. That is x bar plus minus z sigma over root n. Place everything where it belongs, and then you get the answer 49.9 and 50.3, and these answers are given to three significant figures. Now it says, explain why it was necessary to use central limit theorem. Because the distribution was not normally distributed. Because it does not say that it followed a normal distribution. So this is one reasoning that they give. Or another reason, I think this is the best reasoning because that is so obvious. Sometimes they also give the reasoning because population variance is not given. But this could also happen in a normal distribution. So this is the reason why we use unbiased estimate of population variance. So I would focus on the first one, that is because the distribution was not normally distributed. So that is the reasoning of using CLT, central limit theorem. Find the probabilities that the confidence interval in part B is wholly above the true value of population mean. Now this is some basic calculation. That is, this is between these two values is 98%. This above is 1%, this below is 1%. From here to here, this is confidence interval. Find the probability that the confidence interval is wholly above the true value. So the answer is 1%. And if it said wholly below the true value, then the answer is still 1%. So 1% for below and 1% for above. So 4 questions are done. Question number 5. What does it say? It says most plant of a certain type have 3 leaves. However, it is known that on average 1 in 10,000 have 4 leaves. And before I read any further, this looks like a question of binomial becoming Poisson. And maybe there are more parts to it. What is the definition of lucky? That is 1 in 10,000. X follows a binomial distribution, 25,000 multiplied, and this is the other parameter is 1 over 10,000. So N is 25,000. P is 1 over 10,000. NP is expectation, and that boils down to 2.5. Justification, since N is greater than or equal to 50 and NP is lesser than 5, therefore X follows a Poisson distribution with 2.5. That's the first thing. That's the parameter. That is lambda. Use your approximating distribution to answer part B and C. So probability X is less than or equal to 3. That is e raised to power of minus 2.5, 1 plus lambda square over 2 factorial and lambda cube over 3 factorial. That is the answer for this part. For part C, now this is a nice one. After a long time I've seen this. That is using the concept of factorial. So let me first teach you a bit of factorial. When we say n factorial, you even ignore this. If I say 5 factorial, that's 5 into 4 into 3 into 2 into 1. And now if I talk about 4 factorial, that is 4 into 3 into 2 into 1, 4 into 3 into 2 into 1. So can I write 5 factorial is 5 into 4 factorial? The answer is yes. Can I write n factorial as n multiplied by n minus 1 factorial? The answer is a definite yes. Now this is what we'll be using over here, whether in terms of n, whether in terms of k. Probability x is equals to k. That is e raised to power of minus lambda. So that is e raised to power of minus 2.5. 2.5 raised to power of k over k factorial. That is the first working. Probability x is equals to k plus 1. K could be any integer. So therefore this is e raised to power of minus 2.5. 2.5 raised to power of k plus 1 divided by k plus 1 bracket factorial. Now we should also know indices, that is a raised to power of m plus n, that's a power m into a power n. Now they are saying one is twice that of the other. So this one I'm writing in red, that is e raised to power of minus 2.5, 2.5 power k over k factorial. And this one I'm writing in purple, that is e raised to power of minus 2.5, 2.5 k plus 1. 2.5 k plus 1 is 2.5 power k into 2.5 power 1. So that is 2.5 power k into 2.5 power 1. It's a beautiful calculation. And similarly, what about this? The k plus 1 factorial. Can I write this thing as k plus 1 factorial? That should be k plus 1 multiplied by k factorial, just like n factorial is n into n minus 1. So if it's k plus 1 minus 1 is k factorial. So therefore this is k plus 1 and this is k factorial. So now you know exactly what you are supposed to do. So you have this calculation. So let's highlight it. This k factorial disappears. Similarly, 2.5 raised to power of k and 2.5 raised to power of k, that would disappear. Naturally, this thing which is over here, e raised to power of 2.5 negative, 2.5 negative, that would disappear. So on the left hand side, what are you left with? You are left with 1. And on the right hand side, you are left with 2.5 divided by k plus 1. Let's double check to see if something is left out. And one thing is left out, that is this 2. So I forgot this 2. So let me just move this a bit. No, not this one, actually this one. So this one, if I move it a bit like this. So don't forget to write that 2 over here. That is this one. Let me write it in black. That is 2 over here. So when we have this 2, so this is 2 multiplied by this. So therefore 1 is equals to 5 over k plus 1. Therefore k plus 1 equals to 5. Therefore k comes out to be 4. So that is like a pure maths calculation that we are using over here. Now it says the number of lucky plants. Now furthermore question. Now it says the number of lucky plants in a random sample of n plants where n is large is denoted by this thing. So x follows a normal binomial distribution n comma 1 over 10,000. And expectation of x, because it's large, that is n over 10,000. Let me denote it by lambda for right now. Probability y is greater than or equal to 1 is 1 minus probability y is equals to 0, which is 1 minus e raised to power of minus lambda. And this value is 0.963. So 1 minus e raised to power of minus lambda is 0.963. And negative e raised to power of minus lambda is 0.963 minus 1, which is 0.037 negative. Get rid of this negative sign. Get rid of this negative sign. And then take log of both sides. Natural log, that is. So ln e raised to power of minus lambda is ln of 0.037. So therefore minus lambda ln e is some negative value, which is negative 3.2968. Use the unrounded value. Therefore lambda is 3.2968. But wait a minute. What is lambda? but lambda is n over 10,000 because I have used it for simplification. So 3.2968 is n over 10,000. Now when we multiply, so 4 zeros, 32968. So n is 32968 and round it off, that is 33,000. That is the answer, correct to 3 significant figures. So that was a nice question on Poisson after a long while. So question 5 is done. Question 6. This looks like the last question to me. Yeah, this is question 6 and it's a big question spanning over 3 pages. So now question number 6. This is about CR It says the person models the length of time in minutes by which her train is late on any day by a random variable with PDF such and such. Find the probability that the train is more than 10 minutes late on each of 2 randomly chosen days. So at a time you can only calculate for one. So probability x is greater than 10 minutes on just one day is that 3 over 8,000. And this is x minus 20, the whole thing squared dx. The limits are 10 and 20. That is the first part. So basically 3 over 8,000 remains on the outside as a silent spectator. And this you can apply chain rule, that is x minus 20 raised to power of 3 raised to power of 3. Derivative of x is 1, something very obvious, but still follow every single rule. There is 10, there is 20, and use the limits and everything. So this comes out to be 1 over 8. So this is for a particular day, on any day. So probability of greater than 10 minute on day 1 is 1 over 8. Probability greater than 10 minute on the other day is 1 over 8. So both days. So as such, there is no need of using the binomial. That's 1 over 8 into 1 over 8. That is 1 over 64. If you want to use, you can use binomial. X follows a binomial distribution, 2 days, and probability of success is 1 over 8. Probability x is equals to 2, that's 2c2. Success is 1 over 8 raised to power of 2. Failure is 7 over 8 raised to power of 0, which comes out to be 1 over 64. That is the first part. Find expectation of x. Now for expectation of x, what is the rule? So expectation of x, even before that, first multiply this out. So that's a lot of algebra. That is x minus 20 whole square. First expand this. X minus 20 whole square. So that is x square minus 40x plus 220 square is 400. That's the first thing. And then multiply x with x minus 20 whole square. That is x cube minus 40x square plus 400x. Now what is expectation of x? That is integrate between the limits 0 and 20, the full-fledged limits. So this was actually fx and this is your x. So I've already multiplied it on the side, x cube minus 40x square plus 400x dx, and then let me integrate. That is x cube, that is x power 4 over 4 minus 40x cube over 3 plus 400 x square over 2 between the limits 0 and 20. Evaluate it and then you get the answer, that is the expected value. Now coming to the last part, the second last part, that is the median of x is denoted by m. What is the rule for median? Probability x less than the median is 50% of the distribution. So your lower limit is 0, your upper limit is m, your function is 20, x minus 20 I think, x minus 20, the whole thing square dx equals to 0.5, and I'll write this thing as half. So therefore this is x minus 20, this is power 3 divided by 3, between the limit 0 and m equals to half. Let me plug in the upper limit, m minus 20, the whole thing cube. Let me shift 1/3 on the outside, minus 0 minus 20, the whole thing cube equals to half. So this is m minus 20, the whole thing cube, and this is m minus 20, the whole thing cube. No need to open it up. And this is minus 20 cube. So this is actually, I think I forgot the 3 over 8,000. Where has that gone? So that was in the beginning 3 over 8,000, and that is still over here. So let me write it over here, and let me write it also over here. Something like this. Let me shift it over here. Let me shift it over here. So that is 3 over 8,000. Don't forget this. This is 3 over 8,000. Don't forget it. And then you would evaluate. So again over here, this is 3 over 8,000. And this is 3 over 8,000. And this 3 would disappear. And that is actually 1 over 8,000. And this is m minus 20 whole cube minus 20 cube. That is 2 into 2 into 2. That's 8. And this is 8,000. And this is half of 8,000. Got the working? So that's how this working is done. Let me do it a bit more. So therefore, this is m minus 20, the whole thing cube, minus 8,000 is equals to 4,000. And let me double check. So this is 3 and 3 cancels out. 1 over 8,000 as it is. And this is 8,000. Let me double check. Yes, 3 over 8,000. And when we integrate this, so therefore this thing is, this was something else. And this is x minus 20. There is a 3. There is a 3. That's 8,000. M minus 20 whole cube minus 20 into 20 into 20. So this negative will become positive because it's a cube. So this negative would remain as negative, and there was a negative on the outside that gave me an overall positive. So therefore this is positive 8,000, and then take it on this side. So therefore actually m minus 20, the whole thing cube, that's 4,000 minus 8,000, that is negative 4,000. I think that is what the answer looks like. Yes. Hence find the value of m correct to 3 significant figures. So now take cube root. M minus 20 is cube root of a negative number. Cube root of a negative number does exist, and then use a calculator, and then you would get the answer for this thing. And the last part, state one way in which Alethia's model may be unrealistic. What are the limits in this model? The limits in this model are 0 to 20. This is the time in minutes by which her train is late. So what is the limitation of this model? The late can only be for maximum of 20 minutes in Alethia's model. That means if the train for some reason is late for more than 20 minutes, then this model will be null and void, and it will have no real life significance as such, because that is what the model is based on. So that completes May-June 2021 variant 63, the S2 paper, and now more November papers are waiting for you. Stay tuned.